this is an approximate outline of what I'm going to say today. So basically, I will first talk about simple notions like stoichiometry. Most of you should know about that. Then I will talk about the state equation for a multi-species gas. Then I will define enthalpies and energies. At this point, most of you feel that they know what the state equation is for a perfect gas, and they think they know what the enthalpy is. You will see that with a reacting flow, it's a little bit more complicated. And then I will go through the first exercise here, which is computing the adiabatic flame temperature at constant pressure. This is a classical combustion exercise. This will happen in every control you will have. You will have to do that, so you should listen to that part. And then I will talk about dissociations. You will have to go on the website to read this part here, and I recommend that you do it really. It will be useful for the control. And also there's a tool called Adiabatic Flame Temperature Calculator that you should use, which is directly connected with what I'm going to say today. Let's begin by the first simple notions that you need to understand about combustion, which is the global reaction, which we're going to write like this. In general, in combustion, you take nu prime F moles of fuel, you mix them with nu prime O mole of oxygen, they burn and they give you products. It can be more complicated than that, but to first order, this is really what's happening. I will just, on the other side here of the board, give you an example. H2 plus 1/2 O2 gives H2O. That's the level 0 of combustion. So let me introduce right away a notion which is the stoichiometric ratio, which is called S. And S is nu prime O those things here are the atomic weights. So what S is telling you, it's telling you how much mass of oxygen you need to burn fuel. Okay? This many kilograms here of oxygen for 1 kilogram of fuel. If you do that for my example here, you will find S equal 1/2 of 32 for oxygen divided by the mass of hydrogen, which is 2, and it gives you a S of 8. What does that mean here? If you want to do a rocket engine burning hydrogen and oxygen, you need to take with you 8 times more oxygen than hydrogen. 8 kilograms of one for 1 kilogram of the other. Okay, the second definition I need here is mass fractions. The mass fraction of a species K is defined as the mass of K divided by the total mass. So you take a box, you look at the total mass which is in the box for all the species, you look at the mass of the species K, and you divide them, and it gives you the mass fraction. Okay? Now if you want to put that out, you see that you can use S to say that in a mixture which is at stoichiometry, the mass of fuel divided by the mass of oxygen, which is also the ratio of the mass of fuel to the mass of oxygen, is going to be equal to 1 over S. So typically, here in my example, if you have an H2O2 mixture at stoichiometry, you must have YH2 divided by YO2 at stoichiometry equal 1/8. Now, in general, when you burn things, you're never sure that you're going to have exactly 1 mole of this guy for 1/2 mole of this one. So you need to introduce a second notion, which is the equivalence ratio. Which we call phi in general, and phi is YF over YO, the one you have at the point where you are. You don't choose that, it's something which is given to you usually, divided by what you would need at stoichiometry. So this is also equal to S YF over YO. So that's the first classical exercise in combustion. We tell you the mass fractions of fuel and oxygen, ask you to compute the equivalence ratio. So another example is what are YH2 and YO2 in a stoichiometric H2O2 mixture. So to do that, you need to use this equation. That means you need to say that phi is equal to unity if you have a stoichiometric mixture. So it's equal to SYH2 over YO2. Now this is one equation. You have two unknowns. You need a second equation. There's a second obvious equation for mass fractions. I didn't say it here, but it's that the sum of all mass fractions in a gas from k equal 1 to n is the total number of species in your mixture. This thing must be equal to 1. Okay? If you sum all these things, you're going to have the sum of the mass, which is equal to the total mass, so it must be equal to unity. So here you have a second equation, which is YH2 plus YO2 equal 1. So that's two equations, two unknown. I think you should be able to solve that. And this is what you obtain. YH2 equal 1 over 1 plus S, and YO2 equal S over 1 plus S. In the case of H2O2, S equal to 8, so this is equal to 1 over 9 and 8 over 9. And the ratio of these two things, of course, is 1 divided by 8. Most cases, we don't burn fuel with pure oxygen. You don't get the oxygen pure on this world, you get it always with nitrogen. I told you already air is 1 molecule of oxygen and a molecule of nitrogen. A is usually 3.76, depends where you are on Earth, but we will keep 3.76 for this course. So the second exercise would be what are the mass fractions in a mixture of H2, O2, and N2 if the equivalence ratio is phi. So same exercise here. You have now three unknowns: the fuel mass fraction, the oxidizer mass fraction, and the mass fraction of nitrogen. You need three equations. First equation will be YH2 plus YO2 plus YN2 equal unity. The second one, of course, is going to be that the equivalence ratio must be known and imposed. So that's two equations. You still need a third one. The third one comes directly from the fact that we know that if you have 1 mole of O2, you have N2 mole of N2. So we know the ratio of the masses between these two gases. What is it? Well, it's yn2 divided by YO2. It will be linked by the ratio of the molecular weight multiplied by A. Okay, just means that's a simple rule. Huh? One mole of O2 will have this mass. 1 mole of N2 will have this mass, so the ratio of the mass fraction will be exactly this ratio. Now we have 3 equations, 3 unknowns. You can solve that to find this solution. YH2 equal 1 over 1 plus S over phi multiplied by 1 plus A WN2 divided by WO2. And YO2 equal 1 over phi over S plus 1 plus A WN2 divided by WO2. Okay, let's just do the same problem for CH4 plus O2 plus AN2. Classical textbook exercise also. What is the mass fraction of CH4 in a mixture which has a fixed equivalence ratio equal to phi? Exactly the same demonstration, except you have to change S. How do you find S? Well, you need to find the numbers to put here. So this is, again, an exercise you have done many times in the past years. Just to remind you how to do that, you need to know how many CO2s are coming here. It's only 1 CO2 because you had only 1 CH4. Then you need to know how much water you're doing. Well, here you had 2 times H2, so it must be 2 H2O. And then you count how much oxygen you have here, and it gives you how much oxygen you need to put here. 1 O2 plus another 1 O2, it gives you 2 O2. And the N2 doesn't do anything at the moment, so N2 stays here. If you need to compute now YCH4 in this mixture, you're going to find the same expression as before. Except you need to put S equal 4 now, here. If you do the application of that, for example, for phi equal unity, you will find YCH4 equal 0.055. So let me phrase that in another way. If you take a mixture of methane in this room, where you have air, and we open a bottle of gas, and we fill this room with methane, when you will have 5% in mass, 5.5% in mass of gas within this room, then it will be exactly as stoichiometric. So it will be the best moment to kill yourself by igniting your cigarette. The reason this number is interesting is that 5% is not a lot, okay? That means in air, typically, when you have a mixture of CH4 and air, it's basically only air. It's 95% of air, 5% of gas. So that will be useful for us because it suggests that a mixture of methane and air will be not far from air when it comes to questions like viscosity, diffusivity, heat capacity, all these things. So we will use this property in certain theories to be able to simplify the problem, okay? Just to say that basically the fact that we add a little bit of gas in our air doesn't change too much the properties of this air. Okay? Now we're going to go into the state equation. So the state equation is what you need to do any thermodynamic computation. We need to know the link between pressure, density, and temperature. So most of you, of course, know this thing. pressure, density, temperature. And small r here is equal to r divided by w. This is something like 8.31 international units. And this is the atomic weight in kilograms. Classical mistake here. If you want to use, well, you don't want, you need to use international units, so don't put grams here, it's kilograms. Be aware also, if you read French and English books, for all English books, small r is equal to big R, and vice versa. That would be too easy. So if you take an English book, be careful, what they call small r is our big R in France. It's a good way to do big mistakes here. So this is what you've seen before when you had only one gas. Now the problem is that we have what we call a multi-species gas. How do things work when we don't have one gas but a mixture of gases? So that's what I'm going to discuss now. The first thing I'm going to say is that I'm still going to be using the assumption of perfect gases. A perfect gas is basically a gas which has this equation of state. Is that always true? This assumption here is true, I would say 95% of combustion applications. When is it not true? Well, it is not true if temperature is very large, typically more than 5,000 K. Then you will go into more complex things I don't want to discuss here, typically plasmas, for example. And it's not true if the pressure is very large, typically 60 to 100 bars or more. Because there we enter a regime which is called supercritical flows. Where this equation is not true anymore. You need corrections to that. Does this happen in combustion? Well, it happens in rocket. Those of you who want to build rockets, they will have to worry about supercritical problems. If you don't care about rockets, and for the moment we will avoid rockets, this assumption will always be true. So we'll have a mixture of perfect gases. We'll have K equal 1 to n. So we have n species. I have told you, for example, for gasoline or for kerosene, n can be of the order of 300 to 400 species. So let me remind you of a few things about thermodynamic definitions here. For each species K, this species K will have an atomic weight WK. Classical numbers. I know it sounds simple, but we see a lot of people who have forgotten that. So H2, N2, O2, those are basically the four guys you need to know if you want to do combustion. Here, H2 is 2. Actually, I should put 0.002. N2 is going to be 0.028, 0.032, and 0.012 kilograms per mole. Then each of these gas will have a partial density OK. The partial density is what you expect. You take 1 cubic meter of gas, and within this cubic meter you count how much mass you have for the species K. OK by definition is also equal to the total density multiplied by the mass fraction. This is the definition of the mass fraction. It's ρK divided by ρ. Each species will have also a partial pressure. pK. And since we suppose that you have a mixture of perfect gases, pK will directly be linked to ρK by this state equation. Because you assume that each species is behaving like a perfect gas. Now note that the constant which is here now, which we will call also small r k, is changing for each gas. The constant of hydrogen is absolutely not the same as the constant for other gases. Let's take an example. If you look at N2 and H2, for example, RK here is going to be 8.31 divided by 0.028. But if you look at hydrogen, it will be 1.31 divided by 0.1002. Okay, let's start talking about things which are not so pleasant now. The heat capacity. Let's begin by the mass heat capacity. So we'll call that one CP. But since it will be different for all the species, we have to call it CPE-K. Now, the second difficulty in the world of combustion is that sometimes we work with mass quantities and sometimes we work with mole quantities. And it's something dangerous for you when you begin because people tend to mix both. So you have to be aware. Every time you use one of these quantities, you have to know if it's mass or mole. The mole heat capacity, we will call it CPK M. The M comes here for molar. And CPK-M is simply equal to CPK multiplied by WK. Okay, it's the mass heat capacity multiplied by the mass of 1 mole, and you get the molar heat capacity. So if you remember what you learned in the thermodynamic courses a few years ago, you have heard about this guy before. You know, for monoatomic gases, diatomic gases, we have a nice theory, which is the kinetic theory of gases. And kinetic theory tells you, for example, that for a diatomic gas, CPKM is 7/2 of R, which in international units gives you 29. Which tells you, for example, that the CPK, which is equal to CPKM divided by WK, for example, for air or for nitrogen, gives you this number for N2, which is equal to 1000. And this is the number you've been using in most courses up to now. Okay? When you do aerodynamics, you always say CP is equal to 1000, 1004 if it's air. Now the problem with combustion is that temperature varies a lot. And when temperature varies, CPK-M varies too. So how does it vary? How does it change? Well, if you plot here CPK-M, and here you put temperature, the kinetic theory is valid at low temperature. So typically here, you get 7/2 of R and the CPK evolves like this. So it starts there and it goes up. And the change between this point and the value you can have here, for example, at 5000 K, is large. It's typically 50%. And in the tables I gave you this morning, or in all textbooks, you have tables which gives you the CPKs as function of temperature. So that's the first more complicated thing compared to what you used to see, is that now we need to care about the CPK which is not constant anymore. You could think, well, it's not a big deal. Well, you will see that if CPK is not constant, then we have a problem with enthalpy. And I'm going to talk about enthalpy now. If I need some space here. When you ask students about enthalpy, they tell you H equals CP/T. Okay, that's the usual definition. Now you can forget that one. In combustion, it's not the case. So you have to do it at some point. So let me write what people should have told you before. What is the right definition for HK? So that's the enthalpy, the mass enthalpy. So the enthalpy of 1 kilogram of species K, it is something like this. Delta HFK0. Yeah, I know it's unpleasant at the beginning, but you will get used to it. Plus integral of T naught to T of CPK dt. Okay, if CPK is constant, if this thing is 0, then you find HK equals Cp multiplied by the temperature. Okay, you're back to what you've done before. But in the general case, it's not true. This is what we call the enthalpy of formation. At temperature T naught. And this is the sensible enthalpy. So basically what this equation tells you is that the species enthalpy consists of two things. The enthalpy you need to create your species at temperature T naught, and then the enthalpy you need to get from temperature T naught to temperature T. What's this thing here? Well, it's the fact that if you take a complex molecule, it takes energy to build it to its final state. And of course, this is what combustion is about. If you break this molecule, then you can recover this enthalpy. The problem is that in combustion, we need to account for this all the time. Now, where do you get this information and what is T naught? T naught is either 0 Kelvin or 298.15 Kelvin and nothing else. Okay? We could have, in the combustion community, we could have made a deal to use only one temperature of reference. Unfortunately, there are two, 0 Kelvin or 298. It's easy to understand why. 0 Kelvin was the best one. Unfortunately, it's kind of difficult to do measurements there. So people have done measurements at 298, and then they put in the literature either results at 298.15 or at 0 Kelvin. Again, it's your responsibility to look at that. In the tables I gave you this morning, you have a list of the enthalpies of formation for bodies which are pure, like O2, N2, etc. The enthalpy of formation, by definition, is 0. Don't need to worry about that. For all the others, you need measurements. But this is given to you. You don't have to look for it. It's in all the textbooks, in all the codes. This is the data for you. Okay, we have a second enthalpy, which is the molar enthalpy. As you expect, this is the enthalpy of 1 mole of the species K. So this one we will call HK M. And it's simply going to be equal to HK multiplied by WK. So if you write it down, it gives you this result. It's going to be delta HFK 0 multiplied by WK plus integral of T naught to T of CPK WK dt. Now, of course, this is going to be the molar heat capacity, and this is going to be a little bit complex notation. So it's the enthalpy of formation of species K at temperature T0 and M to say it's a molar quantity. It's a very smart notation because you call it M to differentiate between mass and molar. You could have found something smarter, but we stick to that one for the moment. Okay, what about temperature? Well, for all we're going to do in this course, there's only one temperature. And it's the same temperature for all the species. This is fortunate. It will not be like this in more complex cases. But for the moment, we need to care only about one temperature. The mass fractions I have defined, yk equal rho k divided by rho is the mass fraction. I also need to define the molar fraction. The molar fraction is how many moles you have of species n, of species k, divided by the total number of moles. So there is a link between these two guys here. Is that yk, which is the mass, so it's the mass of one mole multiplied by the number of mole of k divided by the mean molecular weight, and this is something I need to discuss now, multiplied by the total number of molecules. So you see that yk is nothing else than wk over w multiplied by xk. W here, this is the mean atomic weight of the mixture. And it is not a constant. The mean atomic weight of your mixture will be something in the fresh gases and something else in the burned gases. How do you find it? Well, here, the sum of the xk is equal to unity, of course, and the sum of the yk is also equal to unity. So if you say that sum of yk equal to unity, here, it gives you sum of the xk wk divided by w equal 1. So it gives you w. W is the sum of on all species of xk wk. So this is the mean atomic weight of your mixture, and it will change. WKs, they are constant, of course. You don't change. The mass of hydrogen is always 2 grams. But the concentration is changing. What you call the composition, which is the distribution of the xk, is changing. So the mean atomic weight will be changing. Okay, so let's start now. I've looked at all the individual species. Now I want to look at the mixture. Suppose you mix all these species. What are the properties of the mixture? So, for the mixture. Now, in the mixture, the density will have only one density, of course. Rho. It's equal to the sum of all the density. So you sum all the partial densities, gives you the total density. The pressure, P, is equal to the sum of the pKs. Same thing. It's not, if you would have to look at kinetic theory to see why it's so, but basically the pressure, or we can add all the pressure because it's a mixture of perfect gases. The temperature, of course, there's only one. Temperature is the same everywhere, so it's T. So by the way, this is going to be a perfect gas which has an R and a W, such that R equal R over W, and such that the pressure, the total pressure, must be equal to the total density multiplied by R multiplied by T. We want also, each individual gas is a perfect gas, and the mixture of all these gases is also a perfect gas, except it has a slightly more subtle definition of its molecular weight. It must be the mean molecular weight here. So there's a second relation you can see right away here, because P is equal to sum of the pKs. So it's equal to sum of the rho k R over WK T. And rho k here is nothing else than rho yk. So if you compare these two expressions, you find here something which is confusing to students, is that if you want to express the molecular weight of the mixture as a function of the mass fractions and not of the molar fraction, you have to equal these two things, and you arrive to 1 over W equals sum of yk over wk, 1 to n. There's nothing magical about it. It's just that here you're working with mass fraction. But if you look at this definition, okay, this one is what you believe. It's a simple average of the yk with the molar fractions. If you want to work with the mass fractions, you have to work with this expression. And of course, quite often we see students believing that W is equal to sum of the yk wk, which is not right. Okay, this is the right expression to use. Okay, so now I need to talk about enthalpy again. So the mass enthalpy of the mixture will be H, the total enthalpy, and it will be linked to the enthalpy of all the individual gases by this expression. It's sum of 1 to n of Hk yk. Hk was given here, and so H is going to be sum of 1 to n of the formation enthalpies multiplied by yk plus integral of T0 to T of the sum of Cpk yk dt. And this is, of course, the Cp of the mixture. So you want to be careful here. When we had only one species, we had only formation enthalpy plus sensible enthalpy. Now we have here an expression where this thing depends now on yk for the mixture. And here we have an average Cp for the mixture. This is for the mass. We can do the same thing for the molar enthalpy. The molar enthalpy is called Hm, and it's going to be sum of the Hkm xk, 1 to n, which is going to give you an expression of, like this one, sum of the formation xk plus the integral of T0 to T of Cp m dt. And this is, I'm going to indicate a few homeworks to do for you. Simple things. You should check, for example, that Hm is equal to H over W. That's easy. Okay, so let's give a few numbers now. You will see that the CPKs, for example, can have really large variations, which is something which is a problem in practice. So let's give CH4, H2O, O2, and H2. You have seen the WKs. I'm just going to write them again. So it's 0.016, 0.018, 0.032, 0.002. So if you look at the formation enthalpies, and those are going to be kilojoule per kilogram, this is what you find in the textbooks in minus 4,000 here, H2O minus. And of course, these two guys have 0. This is a convention. We decided the enthalpy of these pure gases will be 0 at the temperature of reference. And if you go here, look at the formation for the moles. So it's kilojoule per moles. You will find minus 74.8. And here you will find minus 241.8, and of course 0 and 0. Now, life would be easy if everyone on this world would use international units. But as you know, some people still use inches, feet, yards, and calories. So, for example, in the tables you have on your desk, I have given you tables coming from a book by Kenneth Q. And here the tables are given in calories. So it's not a problem. As long as you know that 1 calorie is equal to 4.18 joule, you're fine. But in practice, the problem is that you don't want to mix these two things. And quite often we get into problems because people get confused about what is the data they get. Is it a calorie or is it a joule? It seems very simple, but believe me, it's a quite easy way to make mistakes. So if you look here, be careful, people are going to talk about calories. In English books. French books, you'll find joules. Okay, so let's start now running into some real numbers here by what we call the baseline problem in combustion, which is computing adiabatic flame temperatures. It's really the first exercise you need to do when you do combustion. So it's typically, we fill this room with methane, we ignite it, we let it burn. What's the final temperature? 1,000, 2,000, 4,000 K, whatever. So this is an exercise which can be done on the paper. I'm going to do it on the board right now. And if you want to do it in a more complex situation, I will give you indications of where to find the information to do that. So the problem is the following. We have some fresh, what we're going to call fresh gases. You've got to be careful when we say fresh. Fresh gases, typically it's 300 K, but it can go up to 800 or 900 K in practice in an engine or in a gas turbine because we heat up the gas before we burn it. So we call it fresh, but you wouldn't put your hands in this guy, okay? It would be, you will find it quite hot. Now here we have a mixture of fresh reactants, which we call MK. M can be hydrogen, CH4, whatever, O2, with concentration YK1. This is a data of the problem. This is a given information in the problem. Someone tells you, I have this box at 300 K, and in this box I have put air, and I've added some CH4. Now I ignite it. What's going to be the final temperature here, T2, where we have others will have the same species. Some of them might have disappeared, in which case they will have a 0 concentration. But then generally the YK1 is going to go to YK2. So this is going to be burnt. And burnt in combustion means, from 1500 K to 3,000, 4,000, something like this. I'll come back exactly to what the maximum temperatures can really be in combustion. So to handle a problem like this, we need some way to count reactions. It's like in the bank, basically. So we need to do some accounting. So if we talk first about the global reaction that we're going to have, we're going to write it in a way which allows us to do some simple mathematics behind it. So we're going to say that the global reaction we have here is that all these species which are in the fresh gases, they're going to be combined through one single reaction to give the products. This one will be at temperature T2. This one is at temperature T1. The new MKs are going to be defined even if there is no MK at that point. So let me give you an example of what we call new prime and new. If you look at this reaction, H2 plus 1/2 O2 gives H2O. The way we're going to write it in this formula is to say 1 H2 plus 1 half O2 plus 0 times H2O gives 0 times H2 plus 0 times O2 plus 1 half H2O. 1 H2O, excuse me. So that means that if you put the table H2, O2, H2O, and you want to fill new prime K and new second K, you're going to have 1, this guy, 1 half, 0, 0, 0, and 1. And we introduce another number, which is new K equals new second K minus new prime K. So this number is basically the difference between the species you find on the right side compared to the species you had on the left side. So new K here is going to be minus 1, minus 1 half, and plus 1. So new K is really a balance of this equation. It tells you when this equation moves from left to right, you're losing H2, 1 mole. You're losing 1 half mole of O2. You're gaining 1 mole of H2O. So now, what is the baseline ID to get temperature T2? Well, it's basically thermodynamics which tell you that enthalpy is conserved. Because I'm going to work at constant pressure. For those of you who are going to work on the piston engine projects, for example, you will see that if you are doing a closed box in which the volume is imposed, then it will not be enthalpy, it will be energy. But for what we do here, basically we assume the pressure is constant, so it's the enthalpy is conserved. So it means that the enthalpy of this thing must be equal to the enthalpy of this guy. So that's an equation for T2. It tells us that the total enthalpy of the products must be equal to the total enthalpy of the reactants. Except, remember that the products are at temperature T2 and the reactants are at temperature T1. So, of course, it's not going to be the same. We are going to be working here. When we do this exercise in the combustion community, usually we work with molar enthalpies. We count the enthalpy for all the moles we have. So H of T1 is the sum on all the species we have here of nu prime K multiplied by the enthalpy of each mole of K. So it is going to be integral. No, let me put the delta HF first. The enthalpy of formation of species K plus the integral of reference temperature to T1 of CPK molar dt. And of course, the enthalpy of the T2 will be the sum on all the species multiplied by nu second K, that's the number of mole we have in the products, multiplied by delta HFK 0m plus integral of T0 to T2 CPKM dt. Okay, so if you write that these two numbers are equal, you know everything here because T1 is something which I gave you. The concentrations are given, the moles are given. The only thing you don't know is T2, this guy here. So there's only one unknown, T2. Okay, so that's an equation for T2. Normally the problem is finished. Well, in practice, we're going to do a little bit more than that because it's still a complicated equation. We're going to reformulate it in a different way. Okay, if you look at this equation here, we can take all the enthalpies of formation, these two things here, and put them on the same side of the equation and leave all the sensible enthalpies on the other side. This will lead to a rather simple equation which is written here. It will say that the sum of the new second k integral of T0 to T2 CPK molar dt minus the same thing for the reactants, sum of nu prime k integral of T0 to T1 of the CPK molar dt is equal to sum of the nu prime k minus nu second k delta h fk0 molar. So this has a very simple interpretation. You see here that this is the sensible enthalpies of the products, the burnt gases. This is the sensible enthalpy of the reactant. And this is something which we will call QM. And we haven't seen this guy for the moment. It's the molar heat of the reaction. So QM, if you replace this with nu k, is nothing else than minus sum of the nu k delta hfk 0 m. Now just a comment here. Species have enthalpies of formation. The delta hfk 0m. But reactions have heats of reaction. And it's not the same, okay? To define a heat of reaction, you need to define a reaction. And the heat of reaction is a function of the enthalpies of formation of all the species involved in your reaction. So a typical example for QM, let's do H2 plus 1/2 O2 gives H2, always my simple example here. What is QM? Well, QM here is going to be the heat of formation of H2O, the molar heat. And that's all, because all these guys here have 0 heat of formation. And there will be a minus here. If you look at the table I gave you, you will see that this number is 241 kilojoule per mole. So each time you burn a mole of hydrogen, you are releasing 241 kilojoule. There's a second quantity which is useful to define here, which is the heat of reaction per unit mass, which is just Qm divided by the mass of fuel. If you look at this number for hydrogen, it will give you 241 10 to the power 3 divided by 0.0002, and that's 120 megajoule per kilogram. This number in itself is combustion. It's the reason why combustion works, is that every time you release these two species into water, you release an amount of energy which is huge. Each time you burn 1 kilogram of hydrogen, you get 120 megajoule. That's quite a lot. Okay. As a homework, you should compute Qm and Q for CH4 plus O2 gives product, okay? Simple exercise. With the data I gave you, you have everything needed to do that. Another comment also about this quantity, which is here Q. Q can be used to obtain powers. Why? Well, basically, if a burner consumes m.f kilograms per second of fuel, its power will be simply P equal to m.f multiplied by Q. Okay? And this will give you directly watts. So typically, if you take a rocket engine, where you burn, for example, 10 kilograms per second of H2, the power of this engine will be 10 kilograms per second multiplied by this guy here, 120, 10 to the power 6, so it will be 1.2 gigawatt. So you see 10 kilograms per second doesn't seem like a big number. It's already a big number, but 1.2 gigawatt is quite nice. It's what I said, in the first times we started here, it's like a nuclear power plant. Okay, I haven't finished this demonstration for the moment. I haven't told you how to get the final answer here. So let's do it now. And I'm going to show you 3 ways to get the answer here. First method, by hand, let's say approximate. So here what we're going to do is we're going to say CPK, the CPK which is in this expression, the molar value, does not change with temperature. We know it's not true, okay? We know it's changing by maybe 30 to 40%, but just to get an estimate, we can approximate that and say that CPK does not change. Now, a nice thing about, of course, this integral equation is that if CPK is constant here, you can get it out of the integral. And so this system will become much simpler. We're going to work on that one, actually. So the CPK will come out here, and we'll just be left with the temperature difference on both sides. So that means we'll have sum of nu second k CPK molar on the left side here, multiplied by T2 minus T0 equals sum of the nu second k CPK, it's nu prime here, molar, T1 minus T0 plus Qm. And this you can solve by hand now. Just say T2 will be equal to T1 to T0 plus CPK molar. And here you have sum of the nu prime k CPK m T1 minus T0 plus Qm. So you get the answer. In many theory we're going to use in the future, we're going to use this expression. It's correct if the temperature is not too large. Of course, if the temperature changes by a lot, then it can be a problem. So let's do an example. Again, H2 plus 1/2 O2 gives H2O. And suppose that T1 equals 300 K. So that means the question is, we take a stoichiometric mixture of hydrogen and oxygen at 300 K, we let it burn, what will be the final temperature? Well, you look at this equation, it's a simple one. It's going to say T2 equal T0 plus sum of the new prime K, CPKM. Well, those are the reactants. The reactants, there was only H2 and O2. So if we write it this way, it's going to be the Cp of H2 molar plus 1/2 the Cp molar of O2 multiplied by 300 minus 298.15, that's T0, plus 241,000, that's the Qm, divided by the Cp of the products. By the products, there's only H2O. So it's Cp H2O molar. Now, this is where things get tricky, of course. We made a bad mistake here, a bad assumption, saying that Cp equals constant. Now we need to pick one. The question is which one? If you look at the tables I gave you, I'm just going to copy that on the board here. That's the table coming from QO. If you look at temperature, and here you take CPK molar. Unfortunately, as I said, this is in calories. So mole, that's okay, we'll convert it. At 300 K, the CPK of water is 8.02. And at 2500, it's already 12.56. And at 5000, it's 30.5. Okay. So here we don't have a problem because these numbers here correspond to a low temperature. We can take a constant value, no problem, and a low temperature value. So here we can take 29. It's a diatomic gas, and here also 29 is the theoretical value at low temperature, no problem. But here, now we have to make a choice. Which one do you take? This one, or this one? Well, you can do it at home if you want. I've done it for you here. We find T2 equal 4900 K. If we take Cp at 2500 K. So if we take some kind of mean values for Cp, of course, so we said it's constant, it's not constant, we have to say something about that. And if we take the Cp, which is here, we take the Cp at 300 K, then we found 6000 K. That's a big difference. Why is it so? Because we need to pay for the fact that we didn't want to solve with variable Cp's. We wanted to simplify the problem, so we get a big mistake here. And the problem is, which one should we take? Well, the answer is you don't know. Okay? You don't know because you need to do a better approximation than what's been done here. And so this is why in the past, people have found a better method to do that. And basically, the better method is to forget temperature and to work only with the enthalpy. So if you look at the list, the tables I gave you, you have tables of CPs, but you also have tables of enthalpies. You have tables of integral of CPK molar dt between T0 and T. So if you tabulate those things, then life gets easier. Because if you tabulate those things, the only equation you need to solve is that it's the enthalpy of the products, which is tabulated, minus the enthalpy of the product at T0 must be equal to the enthalpy of the reactant at temperature T1 minus the value at T0 plus Qm. So if you have these tables, of course, that was the problem. But the tables have been created a long time ago by the people working in thermodynamics, so they know how to do that. If you have T1, you can go in the table and read Hs of T1. You replace it here. You can read also Hs of T0. You replace it here. You know Qm, because Qm is the heat of reaction. And then this thing, you get it also from the table. So I should put 2's here and 1's here to make clear that this is for the reactants and this is for the products. So basically, these two things together will give you HS of T2 for the product. Then you go in the tables of the product, and on the other side of this value, you can read the temperature. And you can do that with the tables I gave you. It's a good exercise. I'm not going to do it here. What you do that, you find T2 equal 500 K, something like this, 5,000 K. Which suggests, and it's not stupid, that the right value to take for CP should be somewhere in the middle between the initial temperature and the final temperature. We go from 300 to 5,000. We take a CP at 2,400. It's a reasonable guess. But of course, for industrial applications, it wouldn't be a good idea. It's not precise enough. Okay, so let me finish now with what you are going to do probably most often. So this was the second method, using tables. So now there's a third method, which is called using codes. Of course, this equation is quite simple to solve if you have a numerical tool to do that. So let me just show you how this will look. I have to put this thing back. There are codes. Some of them are free, some of them you need to buy. I'm going to give you names in a few minutes. And this is an example of something you can have access to on the website here. So you go always, same address here, elearning@surfax.fr. You go on the Combustion site. And here you will find this thing called Adiabatic flame temperature calculator. So it's kind of a simple tool. You give it the pressure. You say what is the initial temperature. Here I have used the 300 K for my exercise. You say it's hydrogen. You say that there is no nitrogen. It's only oxygen, no nitrogen in the oxidizer. You give the occurrence ratio. You say calculate. And this guy solves this equation. And he finds 3077. Uh-oh. So now, of course, the question is, well, this thing does not match at all the 5,000 we had here, okay? So this is what I want to discuss now. Why, if we compute completely the adiabatic flame temperature, do we find something which is as low as that? Well, there is a difference between what this thing is doing and what I've done here on the board. This thing knows about all the species which are present in the reactant and in the products, while in my case, I have limited all the demonstration to H2O2 and H2O. Now, in practice, there's something we have to discuss now, which is called dissociations. There is a limit to simple chemistry, which we reach at about 20,000 K or something like this. 2,000 K, excuse me. So, dissociations. When you take H2 and you burn it with O2, you produce water. And so my theory is right up to now. If you look now at the temperature, when you reach temperatures of the order of, let's say, 2000 K temperature, the H2O that you have in the product, the water dissociates into other molecules. So in other words, when the temperature is too large, even the products like H2O cannot remain like this. H2O breaks down into other molecules. OH, for example, H, whatever. And so at equilibrium, when we write that the species are such that the enthalpy of the reactant is equal to the enthalpy of the products, the problem is that the products are not only water. The products are going to be H2O, H2O2, HO2, H, O, OH, etc., etc. There will be about 10 to 15 of them. And now, of course, the code knows that. The numerical codes, they know about all these species. They know that the dissociation takes place And when the dissociation takes place, basically the temperature goes down. Many of these things here, they swallow energy. And so what's happening is that instead of being at 5,000 K, all these species break into other species, and the temperature goes down to this value. So that's a lot, okay? And in practice, in combustion, it's quite difficult to go to very large temperatures, because every time we reach temperatures larger than 3,500 K typically, where the dissociations take place and brings you back to lower levels. So 3,000 K in combustion is quite a reasonable number. It's very difficult to go much higher than that. So it's really the fact that all the species you have here at equilibrium get broken into other species. So of course the theory here is fine. It's just that the basic assumptions of the theory, which is to say we'll have only water, this assumption is not right. Well, is it always a problem? It's not a problem. Dissociations are not a problem when temperature is not too large, let's say 2,500 K. So typically it means that if you remain for air combustion, if you burn only air and not pure oxygen, the methods 1 and 2 will be okay. And we'll use them actually. Even today we'll use these assumptions. It's only when you start burning things with oxygen, pure oxygen, here you get adiabatic temperatures larger than 2,500 K. Methods 1 and 2 are not okay. And you need a much more complex tool which can account for all the species in the burn gases. It's basically due to the fact that most species are okay. At 2,000 K, for example, water will remain water. It will not break into something else. CO2 will remain CO2. Dissociations begin later, when temperature is larger. So there's a homework now for you again. So the first homework is to compute the adiabatic flame temperature, T adia, for H2 plus O2 plus AN2. That means by adding air now, this is burning oxygen with nitrogen and hydrogen. So what will be T add here? And the second problem is to do the same thing for lean combustion. So lean combustion means here F less than unity. So if you don't burn at stoichiometry, of course, the temperature will be less. You don't need to put exactly the amount you need to burn all the oxygen. You can put less than that. Then the temperature will be not so high as in the stoichiometric case.